because Dr. Smith is training on how to break things more effectively currently, I get the honor of introducing Thor. He has been working this semester, and actually a little bit before that, on redesigning or designing a hub to a car. You'll hear about it. You'll see a video that doesn't overheat. So he's been working at it. I helped a little bit. It's a really great project. Take it away, Thor.
Good morning. As I said, my name is Thor Hogberg. I'll be presenting you with a new design for the 1991 Chevrolet Camaro 228 wheel hub. We'll go through the introduction, how I came to this project, a little bit of background, what GM's done from the factory with the wheel hub, what the problem is with this wheel hub, the objective of my project, the static and thermal analysis I did modeling these hubs, the material selection and geometry modifications for the design, and finally the prototype. Jeremy Mullen and I met at a previous internship. He was an engineer I worked under. We found common ground on racing. We both love cars, we both love road racing. So he invited me out on a few race track events, and everything kind of fell in place from there. I've been to 4 or 5 events since then. So imagine yourself, this is Memphis International Raceway. This is kind of ground zero where this project started. You come racing down the drag strip. You reach about 150 miles an hour at the end of the drag strip. Jump on the brakes, trying to slow down for turn 1. This is actually called the carousel if you're familiar with the racetrack. And then you turn the wheel right into the turn. A very serious bending moment occurs anytime you enter a turn. So originally, you can see the original hub here on the table if you want to take a look at it. GM designed an integrated hub that has a brake rotor in the hub all as one piece. This is problematic if you're on the racetrack. If you crack a brake rotor, you don't get to just take the brake rotor off and replace it. You have to disassemble the entire hub and reassemble it again. This takes a lot of time, and it's on the racetrack. Time is important. You want things to go as quickly as you can. What a lot of people do is they'll use aftermarket hubs, such as the aluminum one here, or they will modify the existing hub so that you don't have the integrated brake rotor. So in July of 2013, we were at Memphis International Raceway, and we woke up Saturday morning ready to get on the racetrack, and this has been a reoccurring problem. So we thought we should probably jack the car up. We'll check the wheels and see how the bearings are doing. So we jacked up the front end. The front left tire, we shook it. There was a lot of play in the bearings. Took the wheel off, disassembled it. You can see around this area here, there's a lot of debris in there. When we disassembled the hub, there were big chunks of aluminum in there. And as I said, this is this is an aftermarket hub that he had been using. He's modified this one several times. You can see there's a set screw right there, and this outside piece here. The bearing race had actually been pressed into a piece of aluminum. The bearing race had been pressed into a piece of aluminum that was then welded into the hub. What happened in this case was that the weld broke. Okay. So, if you want to take a look at this. The objective of my project is to design a hub suitable for the conditions found in road racing and compatible with any brake rotor. So this is the work environment here. The spindle is what attaches your hub and therefore your wheel to your vehicle. There's an inner bearing race, which is press fit into the hub, an outer bearing, and an outer bearing race. There's also press fit into the hub. You can see the wheel studs here. This is what your wheel mounts to on your car. The hub has to fit the bearings that come on the car from the factory with the proper interference, and it has to mint to the spindle correctly. The wheel stud pattern has to remain the same, otherwise you can't use the wheels. They won't fit your car anymore. Temperature can have no effects on the material properties of the hub, and the hub must rotate freely without interfering with any of the adjacent parts. This design is limited to the hub. I'm not not designing bearings, I'm not designing a spindle, brake rotor, brake caliper, or anything of that nature. Modeling began with a static analysis. Back in machine design, John Sawwa and I, he's somewhere among you. We started doing a little bit of research. We came across an article published by the Society of Automotive Engineers that explained exactly how this is done in the automotive industry. It's quantified by a point load where your tire meets the ground. There's a lateral force and a vertical force that act at the wheel. This lateral force here is what creates the bending moment on the outside of the wheel. The applied moment that was generated from these calculations was then used in the SolidWorks simulation. You can see here, this is in SolidWorks, this was done as an assembly with the bearing race as a fixture. That's what these green arrows right here indicate. The red arrows indicate the moment that's being applied. And there's kind of a breakdown of what is mounted onto the wheel of. The way Jeremy's car is set up right now, you got the hub, a brake rotor, a spacer that goes in between the wheel and the brake rotor, and then finally the wheel itself. The thermal analysis, this began in November of 2013. I went to a track event. This one was also at Memphis International Raceway. I took Dr. Field's thermal imaging camera, and I was able to get a few pictures of the hub, or the general area around the hub, after the car had been on the racetrack. So the car goes out for a race. There's a cool down lap where they run roughly 60 miles an hour for about 2 minutes around the racetrack. And then another few minutes that it takes to get from the racetrack to the pit. You can see the spot right here. This spot is actually focused on the wheel spacer, and you can see the brake rotor around it. Wheel hub is directly behind that. With the starting temperature of 236 degrees that I found using the thermal imaging camera, we were able to generate a MATLAB code to predict how hot the hub could have been during actual operation. So beginning here and moving backwards, we estimated a temperature of 471 degrees Celsius. This is a reasonable estimate. The brake pads in use on Jeremy's car use compound H. They're from Willwood. And these brake pads operate optimally at around 540 degrees Celsius. So the hub has to be hot, but you don't expect it to be quite as hot as the brake rotor itself. So 471 degrees Celsius is a reasonable estimate. Why is temperature important? Annealing is the process of bringing the material to an extremely high temperature and then cooling it slowly. This causes an increase in softness and ductility. This happens every time the car goes out on the racetrack. The hubs it's using, the aftermarket ones that were being passed around, the aluminum, it started out as an age hardened material, 6061 T6, but it becomes overaged from the annealing and it returns to 6061. All the material properties that were given to the aluminum by this heat treatment are erased. The hub reaches 80% of aluminum's melting temperature. So the results from the thermal analysis and the static analysis were used in a SolidWorks simulation. You can see here that the elevated stress is around the bearing races and all these 90-degree angles and these stress concentrations that occur throughout the inside of the hub. These are good results. This is what actually happened. As with the aluminum hub, the bearing race spun around the inside. That's where most of the stress was occurring. So these are good results. The design uses all the static and thermal analysis that I've previously talked about. I did all these analysis on the aluminum hub and the one that I've done. Material selection. I began with stainless steel. These materials are prohibitively expensive. Aluminum is obviously out of the question. Can't use aluminum. Started looking at other high carbon steels, and I ended up on normalized 4340. This material is in good supply. It's easy to get a hold of, and it works for this situation. I made 3 geometric changes, one of them being ribs on the inside of the hub. This is a cue as to from the original OEM part. If you look at this hub down here on the table, you can see these ribs on the inside. So this is a model. This is a picture of the SolidWorks model that I made. The ribs that I put on extend all the way up to the outside of the flange. I made the outside of the hub, I gave it a greater diameter than the aluminum hub. And due to steel's added strength, I made this flange thinner to reduce some of the weight. So this is kind of like a before and after. This is the aluminum hub that was previously in use, the one that failed in July. And this is the hub I designed out of 4340. You can see the red extends all the way to the outside of the hub on the aluminum. And all the stress, everywhere where the safety factor is below 1 is throughout the inside of the hub where all these stress concentrations are. As you can see, there's significantly less spread on the hub that I've designed. An important thing to remember when you're looking at these results is the hub's not always under these conditions. This is only in a turn where there's extreme heat and the wheels are at their closest point before skidding across the concrete. So this is the most extreme condition. A lot of the time the car is going to be racing down a straightaway when there's not a moment at all, or maybe a very small one, and it's not quite as hot. As I said, I'm not designing the bearings, but there are a few constraints to the hub. Interference is important. The bearing race, as you can see here, is press fit into the hub. This has to be a very smooth machine finish, and this is a very tight tolerance. So this is a very important part of the prototyping process. The backing shoulder diameter, this has to be large enough that it supports the bearing race, but not so large that it interferes with the bearing cage, and it can't impede the flow of lubricant through the bearing. This is the fun part. Prototyping was great. This started with the 3D model. With this model, if you want, I'll pass it around. You can look on the inside and you can see all these stress concentrations that I mentioned before. There's a lot of step diameters throughout the inside of this stuff. The 3D print was used mostly to aid in the production of an actual prototype. Rather than having just a 2D print of a 3D part, which can be really confusing, you have a 3D print that you can look at and a 2D print that you can refer to see all the dimensions. Things make a lot more sense when you have something to hold in your hand. This is the half-scale model. It's not half the size of that scale, but if you compare it to the one that's on the stand there, you'll see that they look very similar. The 1018 cold rolled steel, this was in good supply. I didn't have to order this. I looked at 4340 for producing a prototype. I would have had to have ordered the material. It was a lot more expensive, so I went with 1018. The milling process used a 3/8 carbide end mill for the first pass, 1/4 inch carbide end mill for the second pass, and a 1/4 inch ball end carbide end mill for the finishing pass. Production began on a lathe with 4 inches of this 6-inch round stock 1018. Machined off the outside of the hub first, drilled out the center, flipped it around, machined the inside of the hub. And here you can see this is an unfinished prototype compared to the half-scale model. Milling began at the top. This is actually the back side of the hub. If you want to go there, but this is the part of the hub that's on the inside of the car. Begins at the top, working down. This is after the roughing pass. This used the 3/8 carbide end mill. This is the finished product here. So once I got to this point, I wondered, how am I going to test these things? I don't know if it's actually going to work on a car. I went to the junkyard. I found a 3rd generation Trans Am, which is exactly the same as the Chevrolet Camaro. I removed the spindle from the car, got it as clean as I could, painted it, built a stand, and now this is what's on the table up here. This is an apparatus with which I can take the hub, fit it on, make sure everything works right, spins freely, everything fits. Further considerations for this project would be testing. You could do this with a normal car on normal roads, but best practice would be on a racetrack. The budget for the prototype ended up just over $6,173. And an estimated cost for a set of both the left front and right front wheels. It's around $540. A few people I'd like to thank for this project. Justin Amos, he's the machinist responsible for all of the prototyping. Without him, I would never have been able to see this through to the production of an actual prototype that would have remained a SolidWorks drawing. Jeremy Moen, he's included me on several track events. It's been pretty interesting to see a problem develop and then being able to find a solution myself. My advisor, Dr. Natasha Smith, she's been great. Working with her has made this a pretty fun semester. It's been a fun project. Dr. Field, he helped me with all of the thermal analysis. This is what pulled it all together. Being able to use his thermal imaging camera at the racetrack made it pretty interesting. John Sawa, that I mentioned before, me and him started this project in machine design. We worked collaboratively on the models and the static analysis of the hub. Questions, comments?
Good job. Were you able to make use of your 3D model in generating the code for the CNC mill, or was that all done independently from that?
I was. Professor Nelson was able to get a program called HSM Works. Justin used that program then to, he can probably elaborate more on this, but he used HSM Works to then take my SolidWorks model and make it into a program that the CNC machines could read.
Really fine work, Thor. I'm just curious about the cost of material between 1018 and what was the high spec, 4340? Just curious, what was the difference in cost?
1018 was $116 for 8 inches, and the 4340 was $228 for 8 inches.
Not that bad.
And this, when I priced it, the 4340 was not in stock. I would have had to have ordered it, so I imagine this cost is a little bit higher than it would be if it was in stock.
Did you do the same stress analysis on the 4340 material also? What I'm getting at is the small amount of stress that was internal to the hub.
Is
Yeah,
there
like
areas?
the right-hand picture, would that have been eliminated with the higher strength material, or?
You could select a higher strength material.
That is the higher strength?
This is higher strength.
Ah, okay, yeah, it helps to read the slide.
Yeah, as I said, this is the car's not always under these conditions. So I think the hub would need some testing before you went on to choose a more expensive material.
Would you anticipate this being a long-term fit on the car, or will you replace these hubs on a regular basis?
I wouldn't expect that you would have to replace the bearings. They can wear out. You may have to have a new bearing race press fit in, but the hub itself, I wouldn't imagine you would have to replace.
Very fine work.
Thanks.
Where's this part of the brake on your testing?
This part of it.
The disc?
The disc, I don't have a disc that fits this hub. I don't have wheel studs pressed into the hub.
Would it be on this side of the tan?
Right.
Or you can use slide two if you want.
Break over the middle of the hub.
Thor, can you talk a little bit about your 3D printed part, how easy that was to pull off? Why did you only do a half size? There are students out here who may be interested in doing 3D printed prototypes. types? What was your experience in your whole design process here?
It was pretty painless. Professor Eller helped me a lot with that. Originally, I wanted to print a full-scale model. Go to my budget here. The cost of the half-scale model was just over $56. The material for 3D printing is $15 per cubic inch. So the cost of a full-scale model was much more expensive. If I remember right, it was over $250. So for something to hold in your hands, it's just used as a reference tool. The half-scale model, it worked great.
All right, any other questions?